Yeah, thank you, the associate, for giving me this opportunity to talk to you all. Those of you who don't know me, my name is Kaustubh Rajwade, and I am a postdoc at Astron. And yeah, I guess today I'll be talking to you about, I guess, kind of a rather unexplored parameter space in the PP dot diagram, as my title says, search for ultra long period pulsars. And so, of course, going by tradition, I have to show you the PP dot diagram. So like I said, the current landscape here, right? So I'm showing you the PP dot diagram. Everyone, I think we've heard a lot of talks about, the general population of neutron stars. So you have the magnetars here, and then I'm showing you this little line, this white line, and that's kind of the radio emission deadline. So based on the current models for a coherent radio emission from neutron stars, there's a kind of a limit beyond which you don't expect coherent radio emission from them. So that's why you can see that this part of the PP dot space is rather empty. But things have started to change a little bit recently. So recently we have found a few candidates. Actually, one of them we know is definitely a pulsar, but there are also some other candidates where we can call them as ultra long period pulsars. So what I mean by that is that the period is much, much larger than the typical periods that you find neutron stars at, which can vary from milliseconds to maybe a few tens of seconds. And so now if you plot a few of these candidates here, so I'll talk a bit more about these in the next slide, but you can see now the complete picture that we basically have not explored this part of the PP dot diagram at all. So now there are a few reasons for this. One I already spoke about, which is the theoretical aspect. But what it meant was that until now, because of the whole theory behind this emission, we actually, our astronomers, have barely made an attempt to actually focus on searching our data sets specifically for these long period things. And of course, I'll talk about another very important factor in the next slides as to why we have not seen these things so far. Now, of course, one of the main science drivers here is there a similarity with fast radio bursts here? Now, fast radio bursts are these really bright radio flashes that are coming from cosmological distances. And of course, there are lots of theoretical models that are floating around. And one of the key ones is a highly magnetized neutron star, a magnetar. And there are two repeating FRBs that actually show a periodicity in their activity cycle. And that has really motivated us to say that, oh, is it possible that these FRBs are emitted by neutron stars with an extremely long period? And that kind of, I would say, really kick-started kind of this program or hunt, it got people excited to really look for these ultra long period pulsars or ultra long period magnetars. And so that's what I'm showing here. So here's the PSR 0901 minus 4046. These are some of the single pulses that we see. So we discovered this source with Meerkat, and you can see the large diversity in the radio emission from this source. So there's some quasi-periodicity, there's like some kind of a partial nulling happening here, and it's just a vast zoo. Similarly, this source here, again, you can see a lot of structure here. So this is the 18-minute period source, which was detected by the NWA. One interesting thing about this source is while this thing has been persistent since we found it, this thing is highly transient, meaning it was only seen for 7 or 8 months and then it was never seen again. And so if you compare that with this thing here, that seems like a normal pulse from a neutron star, saying some subburst. In fact, it's not. That's a pulse from an FRB. And of course, bear in mind that the luminosity scales are hugely different here. But at least you can see that there's some kind of an observational similarity in the emission that we're seeing as a function of the observing radio frequency. So I think there is much to investigate there. I think there's definitely a lot of scope to kind of investigate this possibility. And so now I'm going to talk about a very interesting source, which is possibly being missed by our current surveys. So this was also detected by the Meerkat project. I think this was mentioned by Emma and James yesterday. So this was detected in single pulses. So you see a single pulse in the real-time pipeline. And then later we discovered that we had multiple single pulse detections, and it actually had a period of 10 seconds. So here I'm just showing you an array of single pulses that you find from this thing. You can again see it has like 2 components, and each component is like has a lot of structure to it. Again, very similar to the bursts you see from FRBs or radial or magnetars. And then if you look at the image plane, you can see the 2 dates, and there was nothing here on 9th of June. And then you can see, boom, like it's extremely bright on 21st of June. And so we managed to localize it thanks to Meerkat. But I think here's the most interesting puzzle here. This was only seen in one 20-minute observation and has not been seen in any subsequent observations over 3 years. So that really begs the question that how many such sources are we missing just based on the fact that they're extremely intermittent? Intermittent to the point that they're maybe bursting of an hour and then they will not burst for the next 5 years or something before giving out a opinion. So really there's this whole array of periodic radio transients that we're missing out. And then coming back to the ULPMs or ULPPs, as I call them, or many other people do too, is that I think the current time domain surveys are heavily biased against this population. And that really is shown by this diagram. Right? So this is the discovery.
What is ULPP?
Just pulsars instead of magnetars. The ultra long period pulsars.
Oh.
Yeah. So here's the discovery plot of the 76-second pulsar that we discovered. And you can see this is the single pulse that you see in time domain. So that's about half a second wide, and it has a lot of structure. And the only reason we detected this was because it has so much structure that one of the subcomponents was narrow enough for our single pulse pipeline to trigger on. So if you imagine it was just a massive continuous Gaussian pulse, we would have completely missed it. That's just because of how single pulse pipelines work, because we do match filtering. So you have a time series and you convolve it with boxcars of varying widths. And when a boxcar of the right width of the pulse convolves it gives you the highest signal to noise. But you can see in this plot here, this is just showing the fraction of signal to noise that's recovered after the boxcar convolution as a function of the widths. You can see for these 2 sources, it actually peaks at about roughly this duty cycle. And this range basically shows the typical range of trial boxcar widths that are used by current surveys. So you can imagine that if these pulses were pure Gaussians, we would have recovered maybe just 10% of their true signal to noise in our real-time system. So you can see the bias here is fairly obvious. The second bias I'm not going to talk about, like I don't have a slide on, but is that whenever you do a survey with a telescope in time domain, you only look at that part of the sky for maybe 30 minutes, 45 minutes tops, which means that if there's a periodic source that has a period higher than that, you're straight away biased against it. You're not going to see it. And then if it's transient, then just forget about it. So that's why I come to image plane searches. So one of the advantages with an image plane searches is that it's done with an interferometer. It has a very high field of view, and typically these surveys have very large dwell time. So I'm talking about when you do a survey, you're staring at the sky for hours. And so which makes them really the ideal instrument or ideal type of surveys to look for this population of ULPMs or ULPPs. And at the same time, if you say, okay, we don't have the necessary time resolution, but it really doesn't matter for ULPPs. Because if you're trying to look for sources, which have periods of the order of minutes, tens of minutes, hours, typically the time resolution that you can get from an imaging survey is of the order of seconds, which is plenty to find some periodic things like this. But of course, so I guess before I go into this, so normally pulsars follow a very steep spectral index in their flux density spectrum, which means it would be worth doing this survey at a lower frequency because of these ULPPs will be brighter there, which is fantastic. And LOFAR, for example, which is a radio interferometer in the Netherlands, is a low frequency radio telescope, which would probably be one of the most perfect instruments to really carry out such a survey. But there is a big problem there, which is this, which is called dispersion. As you all know, the radio pulses will be dispersed along the band as it comes through the free electrons along our line of sight. And you can see the difference dispersion makes at low-power frequency. So this is the low-power band, and you can see the pulsar. It's a really bright pulsar. If you just observe it without correcting for dispersion, this is how the time series looks like. Thanks. And yeah, you can see the big difference. And again, I think this plot is kind of just emphasizing on that fact that it's really important to correct for this, especially if you're doing a survey like this at low frequencies. And so I'll just quickly go over this. So this is what I've been working on over the past few months. So this is the low power radio dispersion pipeline. So what we're trying to do is we're actually running dispersion on the radio images that we get from low power. So far dispersion has been mostly done on time domain surveys where you just have a time series, but instead here, you can see that you can actually disperse the radio images that you get across frequencies. And you can do a very similar periodic search that you do in a time domain survey, but just on radio images to basically maximize the sensitivity. So you can see a quick proof of concept here. So I simulated like a transient in images, and this is basically when I just integrated without doing the dispersion correction, and this is after. And you can see that you already get a massive boost, especially at these frequencies, even for TMs as low as 100 or 150. So the last thing I'm going to talk about is the low-power galactic plane survey. So we basically applied for some time to do a pilot survey of the galactic plane. So this is just 6 pointings. Each pointing we integrated for almost 4 hours with the best time resolution of 1 second. I think this is the part of the galactic plane that we're looking at. And just the idea is to test this out and see if we can actually manage to find a couple of these ULPPs. Because this will kind of lay the groundwork for doing like a much bigger survey of the sky with not just current instruments, but also future instruments. And so, yeah, so here's kind of the first images from the survey. So the survey ended end of last year. And so I've just made a mosaic of like 3 of the fields. So this is the galactic plane at 150 megahertz. Let me tell you, it is painful to image it at 150 megahertz. But you can see there's like lots of things here, and I've already almost run out of time, but there's lots to do here. It's not just ULPMs or ULPPs, but there's a host of other galactic plane science that can be done with this data set. So this is the ongoing work and plans. Like I said, the observations are done, and we're now starting to do the data analysis and getting light curves and searching for transients. And of course, the next thing to do would be to run a proper dispersed periodicity search on these data. So let me leave you with my summary. So I think it's a very effective way to use imaging surveys to look for this completely unexplored parameter space in the PP.dot diagram. And I think doing dispersion searches at low frequencies can be an effective way to really maximize the sensitivity towards this population. And I'm planning to use this similar search technique, not just on the current surveys, but also on the next generation telescope. So yeah, thank you so much.
Questions, Andre?
How many ULPPs do you have now? Or better to say, how many can you talk about?
Yes. So yeah, there are 2 that we already know of, which are published. The 76-second one and the 18-minute one. But there are, I won't say the exact number, but there are a couple more that are coming out very soon. Yeah.
Hey, you mentioned at some point you want to do periodicity search at some point. How are you planning to do that exactly?
So what you do is that you have a 4-hour observation, right? You split it up into 10-second images over frequencies, and then you run a dispersion search, and you basically get an image time series over every DM trial, and then you can run a periodicity search of that.
But will you still suffer from like red noise or something like that normally we see in normal time series?
Yeah, of course. I mean, yes, there is that question, but I mean, but the fact that you are at 150 megahertz, if you don't disperse, you're basically going to smear everything, like literally. So if you want to go to deeper or higher DMs in the galactic plane, which is where you expect a lot of these things to be in, so then you have to do that to improve your sensitivity.
Vivek?
Are you also searching across polarization or Stokes parameters?
I wish I could. Calibrating polarization with low power on the galactic plane is a massive challenge. we have just about managed very like literally last week to calibrate for the circular polarization. Linear is a whole like beast, right, of its own, because there's the added dimension of Faraday depth. So even before you can do a linear polarization search, you actually have to first do it on every Faraday's rotation slice. So it's a bit complicated, unfortunately.